virtual environment in the computer, the way in which we might simulate physics within the virtual environment, or carry out, track the movement and interaction of objects under the laws of physics in the environment. Now, we're just going to do we're just going to consider this in a fairly simplified way, and just do kind of an introduction to it. I mean, you could do a whole course on simulation of physics. It's a big topic. Lots of the modern games now, for instance, when interactions happen in the game, so when crashes happen or impacts happen from one object into other movable objects, a lot of the time they aren't simply carrying out pre-programmed animations of collapses or how the object should move. The computer is actually, to a greater or lesser degree, sometimes simulating the real physics to give a more realistic kind of, more freedom in the interactions that can happen in the game. Okay? So some of the issues underlying that, or some of the kind of beginnings of that subject, is what we're going to look at today. So first of all, we reviewed some of the principles behind mechanics in a three-dimensional setting, which we'll need to use. So we have the concepts of position, velocity, and acceleration to describe the movement of an object. And we're still going to be talking with respect to usual coordinate axes and so on. Typical units we'll be using will be meters and seconds. So meters for positions or distances, meters per second for velocities, and meters per second for accelerations. So if we use the conventions of that, the position vector r, or the vector r gives the position of an object at time t in 3 dimensions, then v of t and a of t will be the velocity and acceleration of the object, respectively. Now we know from basic principles of mechanics and vectors that these quantities are related through calculus. So velocity is the rate of change of position. So v is dr dt, roughly, and acceleration is the rate of change of velocity. So acceleration is dv dt. Or run the two together, we get acceleration as the second derivative of position, d2r dt squared. And of course, note that in my symbols there for these quantities, I'm using heavy bold type. So I'm using vector notation for r, v, and a. Okay? So these are referring to objects in 3 dimensions. So these are 3-dimensional vector quantities. So the position, so vector r of t is a vector valued function of time. And if you need to, you can think of the 3 component functions that involve there. So there'll be an rx of t, a function of t, giving the x component of the position of the vector of the object at time t. Similarly, you'll have component functions ry and rz. And the differential operator ddt acts on the vector r, it acts on it in a component-wise fashion. So you take the meaning of the derivative of the vector valued function r with respect to time it's that vector you get when you differentiate with respect to time each of the component functions. Okay, so drx dt, dry dt, dr. So, straight away we've got our first exercise just to investigate some of these things, which is exercise 8.1. I'll put this on the screen. So it's just a first exercise to work with these. So what do we have to do here? Here we're asked to consider a particle whose position r at time t is given by a vector value function r of t here. And it's given as a quadratic in t, so it's vector e plus vector f times t plus vector g times t squared. And we're given the specifications for the e, f, and g vectors, and we're just asked to derive the velocity and acceleration of the particle. So we can have a look at this. So 8.1. So we've got r of t. Vector r of t is the way it's given, e plus ft plus gt squared. So in particular, at time 0, it'll have position vector e. So e, if you like, of e as being the initial position of the object. So we can express velocity. The velocity vector v of t as vector v of t is e dt of vector r of t. And we don't have to go down to the two-component or to the component level straight away. We can just differentiate this, keeping it in its vector form, because the vector f and the vector g, those are constant vectors. They're given in the question. So we can just differentiate it there, and it will give f plus 2g times t. And the acceleration, which is vector a of t, is given by vector a of t is just going to be d dt of vector v of t. So that will give the acceleration as being 2 times vector g. Okay, just taking this expression f plus 2gt, differentiating it with respect to t. The vector f on its own is just a constant. It doesn't depend on t. So when you differentiate it, it goes to 0. And then 2 times vector g times t. Well, derivative of something times t is just whatever that constant something is. So from these expressions here, you can say what the velocity vector is. So the velocity vector is the vector f, which is given the equation is 160 plus 2 times g, which is 1 minus 20. So this is going to be 1 plus 2 is going to be 3, 6 minus 2, 4, 0, 3, 4, 0. Sorry, there's a t here. Sorry, there's a t. What I'm trying to say. Sorry, this is 1 plus 2t is the first component here. 6 minus 4t. Yeah, the velocity should still depend on time here. So here you can see this will be the function vx of t. This will be the function v sub y of t, if you like. And up there is v sub x of t. And this here is v sub y of t. V sub z of t is 0. No, I'm not putting the vector twiddle underneath these now because they're not vector quantities, they're just scalar quantities. And the acceleration, well, this is just 2 times vector g, so it's just 2 times vector g is 1 minus 20. So just 2 minus 2. Which, interestingly, note, so i.e. we've got constant acceleration. So a vector with position, an object with position vector which goes up to order 2 in time, or quadratic in time expression, that's going to be an object moving under constant acceleration. So that's just a first look at differentiating these vector expressions. So section 8.3 here, we start to look at different ways in which objects might be moving in our virtual environment. Okay? So obviously, depending on what's going on in the environment, there will be, potentially many forces acting on the objects in the environment. You might have user input controlling forces that are applied to the object. For instance, if you're piloting a spaceship in a virtual environment or something, your user input will affect, say, the engines of the craft, the rocket engines or whatever, craft. The object might be colliding with other objects in the environment, so subject to forces, collision forces. It might be moving under the influence of gravity and so on. So depending on how many forces are at work or how detailed the simulation of the environment is, the simulation could be carried out to a range of complexity. And very often, when you've got a number of forces acting in combination like that, very often it's not possible to extract exact solutions of those kind of simulations or situations. And very often, approximate or numerical techniques will have to be used. Although we're only going to look at some fairly simple situations here, which do have exact solutions, can be solved exactly using calculus. We'll show, nevertheless, how some basic ideas of numerical simulation might operate. So the first kind of situation we're going to look at is so-called constant acceleration. This is where the force on the object, which forces are things that accelerate objects, this is assumed to be constant. We're only going to deal with situations where it's constant, or at least treat the simulation of it where it's constant for time. I'm looking at situations where you're simulating the environment between one frame of the animation and the next, where the acceleration is assumed to be constant. So we'll just set up some notation and equations here. We're going to let S denote the displacement of the object during this period, and the t is the time variable for the period. U is going to be the initial velocity of the object, and v the final velocity. So you can see how these things are related now. The final velocity is going to be whatever the initial velocity was plus t times the acceleration. The acceleration is the rate of change of velocity, so how velocity is changing over time. So if it's constant acceleration, and you multiply that constant acceleration by the length of time t, that gives you the change in velocity. So the new velocity will be the old velocity plus acceleration times time. And then integrating that one step further, we'll get that the distance moved by the object, will be the velocity times time plus a half acceleration times t squared. So this is, I was just looking at that, wondering, did I need to bring in some initial constant of integration, some initial position of the object? But no, here S is denoting the displacement of the object over the time period t. So S is the change in position. Change in position. So I don't need to bring into this equation here what the initial position was. So this is expressing the displacement, the distance moved in terms of the old velocity and acceleration. But there's an equivalent formula if we use, well, if we make this substitution for it, you see you've got u times t here, but we've got this equation up here relating v and u. So we could use that first equation to substitute for u in the second equation. We could replace u by v minus at. And then this would become s is v of t minus a half at squared. Okay, so this is referring to the distance that the object has moved, but with reference to the new velocity of the object, the final velocity of the object, v of t, in the constant acceleration. Or yet a third expression for it would be here a half of u plus vt. So this is where we just we use the first equation to we take this second expression here in the s and replace the acceleration using the first equation. V equals at. So you need to multiply by t as well. So bring it together, then you've got a half of u plus v times t. So this is expressing the distance moved just in terms of the two velocities, the initial and the final velocities. Okay, so we might look at exercise 8.2 here to illustrate how some of these ideas can be used. Okay, so we're not yet into talking about how the virtual environment simulates or approximates any of this stuff, but that's coming in a moment. And so just to do some work with these equations, we're going to think about a train leaving the station at time 0 and accelerating at a constant rate of acceleration there, 0.5 meters per second, for 30 seconds. It's then going to travel at a constant velocity for a further 100 seconds before beginning decelerating then after 100 seconds at a rate of 2 meters per second until it comes to a rest. So how far has the train traveled by the time it comes to rest? So we can deal with this kind of question. One, so 8.2. Now this isn't we're talking about a train moving along a track, so this is kind of a simpler one-dimensional motion. So not really using the full vector description. So what were my vector quantities s, v, u, and a, and so on in the equations we've just looked at? We can consider they're simpler versions of those equations where the objects s, u, v, and a are just simple scalar objects. Okay, so we're just going to look at motion along the line. So we want to track what's happening to this train, and there's three phases. There's the acceleration phase at the beginning, then the middle kind of coasting phase, the middle constant velocity phase, and then the deceleration phase. So looking at the acceleration phase first, and we've got constant acceleration of 0.5 for a time period of 30 seconds. Now the train is leaving the station, so we're presuming that time 0 it's got initial velocity, but it's not stopped in the station. So it's just moving from initially at rest. And then v, the final velocity here at the end of this acceleration phase is given by v is u plus a times t. So, well, u is 0, a is 0.5, so v should be 15 meters per second. And the displacement, the distance the train has traveled, displacement of the train is given by s. Well, since we've got u and v to hand, we can make use of this simpler equation. half of u plus vt. So it's a half. Well, u is 0, v is 15, and t is 30. So this seems to be just 15 times 15. So this would be 225 meters. Okay, we're multiplying velocities by time, so multiplying meters per second by seconds, so it comes out as meters, as we expect, because we're talking about the distance traveled, or the displacement. The displacement. So that's the situation. So we got the final velocity v and the overall displacement s that's happened during the acceleration phase. So then you've got the coasting, or constant velocity phase. So now we should take u as being 15. And it's moving with constant velocities. There's no acceleration, so we should take v as 15 as well. V is the final velocity. The final velocity in this coasting phase. And we're told that it's coasting for 100 seconds. So the only thing we need to work out, that a is understood to be 0 here, because it's coasting, it's just moving along at a constant velocity. The only thing to work out then is the distance traveled, which again we can do as a half v plus vt, which will just be 1500 meters, or 1.5 kilometers. Okay, so half 15 plus 15 times the 100 seconds this is taking place of. So this is then followed by the deceleration phase. And for deceleration phase, well, the initial velocity, so just before it starts decelerating, its velocity will be 15, like we were told, so it's coasting at 15 meters per second. And the deceleration, or the braking of the train, we're told, takes place at a rate of 2 meters per second. Now this is the brake, so assuming it's moving in the forward direction is the positive direction, we think of the acceleration here as being negative. Okay? It's slowing down instead of speeding up. So it's in the opposite direction to its original motion. So the a is -2. Now we're wondering how long it takes to come to rest. So the final velocity would be 0. We want to track how long it takes to come to rest, and our object now is to find t. In the previous two phases, the t value was known. We were told it's accelerating for 30 seconds and then coasted for 100 seconds. So how long is it going to take to decelerate? So for solving this, we should maybe look back at those equations we had and use the one for v in terms of u and acceleration. Because we know v, u, we know the acceleration, but we don't know time. Okay. So we use the equation u equals final velocity equals original velocity plus acceleration times time. We know the final velocity to be 0. We know the initial velocity was 15. And the acceleration is -2. And the time we don't know for the time being. But of course, we can solve that down. Time is then 15 over 2. 7.5 seconds. And the question, if you look at exercise 8.2, it also asks us for the total distance. How far will the train have traveled by the time it comes to rest? So we need the distance traveled for this deceleration phase. So the displacement in this phase Well, we could take that as s being the half of u plus v times t. There's a half times 15 times t is 7.5. So this would give us, well, multiply those out, you get 56.25 meters. Now that's just the displacement in this phase, so the total displacement across the three phases is just the sum of the three displacements. So the total displacement is just to add up the three displacements we've got. So 225 plus 1500 plus 56.25 meters. Which equals whatever it equals, 2,781.25, just over 1.7 kilometers. Okay, any questions, any queries on that? Or? Okay, so that was just one-dimensional. So let's, exercise 8.3 goes back to kind of working in 3 dimensions again. So let's look at that, exercise 8.3. So consider a motor around fired with a certain velocity v. We get a 3-dimensional velocity vector, so 10, 65. Now, if we're still using our computer graphics convention for the axes. So it's a left-handed rule with the y-axis being the vertical axis. So you see its main velocity is in the vertical direction there, the 60. So it's mainly going up. It's going a little bit in the x and z directions. So it's a mortar. So this unpowered thing. So it's like a cannonball or something. So it's shot with some initial velocity, and then it's moving under the influence of gravity, so it's going to come back down. And we'll assume that any effective air resistance can be ignored. So for a small, very heavy object, that might be a good assumption for a short flight time, anyway. So the force of gravity then is, of course, gravity. The gravity acceleration at the Earth is 9.81 meters per second, approximately, towards the center of the Earth, so in the negative y direction. So that's why the vector g there is minus 9.81 in the y direction. So look at 8.3. Now, what is it asking us? Where will the thing land? Where will it land? So the acceleration is this vector g, which is 0 minus 9.81, 0. So if we integrate that, then we can say that the velocity can be found by integrating this. So we'll get velocity at time t is going to be g times t plus a constant of integration. This constant of integration will be v naught, the initial velocity. But we're provided with the initial velocity as this vector v in the equation. So my velocity vector now is this g vector times t plus my original velocity vector 1065. And we want to know yeah, I want to know where it's going to land. So we need to know what its position is. But the position r of t can be found by integrating this. You don't necessarily have to remember what all these mechanical equations are. You just need to remember this, really this one basic property that you pass from acceleration to velocity by integrating, and velocity to position by integrating, and you go in the other direction by differentiating. So the position of this object at time t, the mortar at time t, will be 1/2 times the acceleration vector times t squared plus the initial velocity times the times t plus maybe some initial position. This is the constant of integration. It's a constant of integration, constant vector of integration. We're doing the vector description now. And well, this is I'm kind of free to choose this. We'll assume that the initial firing position is the origin. And that makes sense to use that description. But assuming that the initial position is at the origin. Now, there's nothing screaming out at the moment at me where it's going to land, or how long it's. I mean, t still seems to be an unknown parameter. It's going to be flying for time period t, but how long is it going to be flying for? Well, assuming, we have to make some additional assumptions. I mean, if you fire it at a mountain, it's going to fly for short times. It's going to hit the high ground of the mountain. Whereas if you fire it into a valley, it'll fly for longer times. It can fall into the valley. So you have to make some assumption about what the topography is like. So we'll assume, or are we told in the question? Yeah, we're assuming a flat plane. So this is fired on a flat plane. Okay? So it's fired from a height of 0, say, fired from the ground. Well, yeah, because if I'm assuming that the position of it at time 0 is the origin. So I'm assuming that it's fired from the origin. So the mortar will be in the air until its y position, ry of t, equals 0. So this is going to allow us to find t. So if we isolate the ry component, the second component of the position there is minus 9.81 over 2 times t squared plus 60 times t. The second component, so we just read it off here. We're adding these two vectors together, looking at the second component here. We want this equal to 0. And that can be factorized. This is t times minus 9.81 over 2 times t plus 60. Well, that clearly has two solutions. T equals 0. Well, that's when it's at position 0 at time 0. That's when it's fired from the ground. It's the other time that we're more interested in, which is 120 over 9.81. Can I work that out? No, that was. Which is whatever it is, approximately 10, a bit over 10, or 11. 12 or 13 or something. But that's our flight time. This one is the flight time. So we can get the position where it lands then. So the landing position the landing position is r at this time value. So it's r at 120 over 9.81. So it's going to be half of 0 minus 9.81, 0 times this quantity squared, plus 1065 a vector times this quantity. Okay, but then it's just an evaluation. Okay, so you just evaluate these two vectors using a computer and a calculator, and you'll get your final position. Okay, so that's a couple of examples of objects moving under constant accelerations. Constant acceleration, gravity there in that second example, and in the first example with the train, okay, moving with, okay, it's in 3 different phases of motion: accelerating phase, a coasting phase, and then a decelerating phase. But within each of those phases, it was moving constant acceleration. Okay. We can use these equations derived from the velocity, position, and acceleration to solve various questions and to track the motion of track the motions of these objects. Okay. So now we come on to considering how this motion is simulated by the computer in simulating the virtual environment. And well, historically anyway, not really historically, I mean, with operating computers, it's always a battle. I mean, the computers have finite resources of computational power, so it's always really the practice of programming the computers is often the practice of squeezing the most out of the available resources that the computer can provide. So we want to consider, what kind of approximations we can use to track this kind of motion. And as well, the computer could be simulating the motion of many objects in the environment. Okay, hundreds, thousands of objects. So it's going to have to do these calculations pretty quickly. So in this paragraph here on page 53, talks about there's these two kind of models that we could use when we're doing this simulation. And they're constant velocity model and constant acceleration. Now what it's talking about here is the way the environment simulates the motion in one bound. So generally think of that as simulating the motion of the objects between one frame of the animation and the next. So of course, to produce that animation, it will know the positions of the objects at the start of the bound, because it will have calculated the previous frame of the animation. So it knows the current locations of the objects. What the environment is doing is calculating the positions of the objects for the next frame of the animation at the end of the bound. And there's a trade-off here between, we can make the simulation more exact by using more computations, more calculations, more of the computation power. Or we can, by allowing the approximation to be not so good, we can use less calculations, use less computation power, which will enable us in the same amount of actual time by the clock on the wall, we can simulate the movement of more objects. We can simulate the movement of one object using less computational power, then in the same amount of real-world time, we can simulate the movement of more objects. So what are these constant velocity and constant acceleration models? Well, in the constant velocity model, as its name suggests, the assumption is that whatever changes in velocity in the real world, moving under the influence of a force, so typically moving under the influence of gravity, the velocity is going to be constantly changing. But the constant velocity model assumes that, well, for the course of this one band, course of this calculation between frames, we're going to assume that the velocity does not change, that the object is the same velocity throughout the band. Now that doesn't correspond with reality. In reality, every moment the velocity is changing. But for the purpose of this assumption, in the constant velocity model, we assume that it doesn't. Now we do update the velocity at the end of the band. So for the next frame of the animation, we will update the velocity using whatever acceleration is at work on the object. But for the course of the band, figuring out the position of the object, we're going to assume that the velocity was constant over the course of that band. Then the constant acceleration model is more detailed. It does take into account the acceleration, the way that the velocity is constantly changing across one band. So in the constant acceleration model, we do allow, or we do track the change in velocity of the object over the course of one band, so between frames. But we make the assumption that the acceleration that's applied to the thing is fixed. Acceleration is constant over the course of that band. The acceleration might be updated at the end of the band. So you might have a new value of acceleration for the following frame, okay, because of what's going on in the environment or because of user interaction, changing the thrust applied to one of the rocket engines or whatever. So the acceleration might change and have a new value for the next band. But for the simulation over the course of the band, between frames, in the constant acceleration model, the acceleration is assumed to be constant, but the velocity is assumed to be changing. So we've got a little bit of a description here showing you the equations that might be used in the constant velocity model versus the constant acceleration model. So in the constant velocity model, so this index j, the index j is going, say, counting from 1 to n. So this is calculating n frames of the simulation. Okay. Delta t is the duration of one band. No, J here we're using to index the objects. J is indexing the objects in the environment. Okay, so one of these equations for each object. Each individual object has its own velocity. Okay? So Vj is the velocity of the object J at the beginning of the band. Delta t is the length of the band, so it's the short time interval, fraction of a second or whatever, between frames of the animation. So the displacement, the distance traveled, or not distance, the displacement vector, we're simulating a three-dimensional environment. The displacement vector of object J will be its velocity at object J, the velocity that it has at the beginning of the band, times the length of the band. Okay. And so then we can have this expression here. So the position of object J at the end of the band will be Qj, which is its initial position, plus its displacement Sj. So this equation here is how you update the position of the object and find out the new position, Rj, for the object at the end of the band, as its old position, the position it had at the end of the previous band, beginning of this band, plus the displacement that it undergoes in this band. And in the constant velocity model, the displacement is simply the constant velocity vector for this bound times the time. And then, as I said, at the end of the bound, the velocity should be updated to its new velocity that it will have for the course of the next bound. Okay. And while assuming constant acceleration taking place, that would be done with the kind of equation we've seen before, as the new velocity is the old velocity plus the acceleration times the time. Now, the constant acceleration model is more detailed. So here again, S is the displacement of object J. Sj is the displacement of object J during the bound. But now we're tracking using U and V, we're tracking the initial velocity of the object at the start of the bound, and we're tracking its velocity throughout the bound. Okay, so Vj is the final velocity, then maybe in these equations, yes, so like the previous equations, these equations, it probably should be delta t rather than t. Delta t, the time bound. So it should be delta t squared. So the velocity of the object at the beginning of the bound is uj, its velocity at the end is vj, and this is the relationship between vj is the initial velocity plus the constant vector times the time period, delta t. But now we're updating the position of the object using its displacement sj. But now its displacement is taking into account the acceleration that takes place over the bound. Okay, so it's not just having this very restrictive. Before we had the displacement was the velocity times the time period. That was the constant velocity picture. Here we're not assuming constant velocity over the course of the bound, so we're taking into account the effect of the acceleration. Delta t here as well. So all those t's become delta t's. So just before the break now, we can have a look at the exercise 8.6, which compares the performance of these two models. Okay? And we think of them both as approximations of the real situation. So we'll think of this setup here, and then we'll carry out the simulation using the computer, and we'll observe the different performance of the two models. So let's just read the setup first of all. So the setup is in exercise 8.6. So it's about a rocket going through space undergoing deceleration. Okay. So think of a rocket ship. It's firing its engines in order to decelerate and reverse direction. We assume the rocket is out, say, in outer space somewhere, so it's not near any sources of gravity. So we'll assume that there's no gravitational force. So the only force is that produced by the rocket. And so the ship is moving in a certain direction, and we're assuming that it's going to fire the rocket. You know, the rocket is going to be face straight ahead. So it's going to be decelerating in exactly the opposite direction of its motion. So it's the best way to slow it down, and reverse its direction the quickest. So it's moving here towards the door. It's going to have its rocket facing the door and fire the rocket to produce a force going back straight in the opposite direction. That will slow it down until it's momentarily stationary, and then it will start to accelerate away in the direction it wants to go. And so we'll give ourselves some numbers for this. So we'll assume, because really that just reduces to one-dimensional motion. It's moving in a certain direction with a certain velocity. It's decelerating down to a stop and then moving back in the opposite direction. So we'll assume that it's at the beginning of this simulation, it's going to be at position 0 with initial velocity 5 meters per second. And initial acceleration of -4 meters per second. And the rate of change of acceleration we're going to assume is -8 meters per second. So that -8 there is the derivative of acceleration. And we're going to plot the position of the rocket over the time range 0 to 1.5 seconds. And we're going to use a time band of 0.05 seconds, so 1/20th of a second, 500th of a second. Okay, so we're just simulating an overall time length of 1.5 seconds, but we're using a band so that time length between frames of the animation, so to speak, is 1/20th of a second. Okay, so let's do this on the computer. Using the two different models and see how they perform. Okay, so I've got a prepared worksheet showing this. Now, what we expect from beforehand, we expect the constant acceleration model to produce a better approximation to the true picture compared with the constant velocity model. Okay. So the constant acceleration model is taking into account more information. So you'd expect the simulation provided by that to be the better one. Okay. So let's see what we've got here. Okay, so I've done this in Sage, but again, something very, very similar. Really all I'm using is just some algebra with the quantities and some plotting commands. So you can easily do the same thing in MATLAB as well. So first of all, I type in all the information given. So I've got a rate of change of acceleration. So that dA dt is just a variable name. It's not actually, the computer doesn't know that that's the derivative of acceleration. So it's just dA dt is a variable name, is -8. That's the rate of change of acceleration produced by the thrusting engine. Initial position x0, again, x0 is just a variable name on the left there. We set x0 equal to 0. V0 we set to 5, so that's the initial velocity. The initial acceleration, A0 is -4, and the time bound dt is 20th of a second. Now, the full simulation, I better execute those. Set those values. I'm going to use t as a symbolic variable. So next I set up, so this function, this acceleration function a of t, this function v of t and x of t, this is going to be the real physical mechanics that takes place. Okay? So take the rate of change of acceleration and I integrate it. So I integrate it by multiplying it by t and I add on the initial value, a0, it's the constant of acceleration, that's the initial acceleration. Then I integrate again, so the velocity is going to be a half of dA dt t squared, we'll say 0 times t plus v0, v0 is the initial velocity, and then I integrate again to get position, so you got rate of change of velocity over 6 times t cubed, rate of change of acceleration divided by 6 times t cubed. Initial acceleration divided by 1/2 times t squared. Initial velocity times t and initial position. So I set up those functions. Just have a look at the function x. It should be a cubic in t. It is, and we'll plot it to see the full mechanics. So this is illustrating the one-dimensional position of the rocket ship. So the rocket is traveling in the positive direction, and it travels out to a distance, well, approximately 2, or maybe exactly 2, I'm not sure. Approximately 2, and then for a moment it's stationary, and then it starts to travel back again. So its position starts to decrease. So at this time period, so somewhere just before 1.4 seconds, it passes its original position, but going in the opposite direction, and it continues to accelerate and continues to move out in the opposite direction. Okay, so this is it graphed between t from 0 to 1.5. Okay. But to calculate each of these positions, it's had to evaluate a cubic, which is more expensive. Evaluating a cubic is more expensive than evaluating a quadratic or evaluating a linear function. And if it has to do this thousands of times for tracking the positions of thousands of objects in the environment, perhaps it's computationally expensive. Okay. So now we're going to produce the simulations of this. So we'll take this first graph as being kind of the real underlying behavior. And we're going to attempt to simulate that using either the constant velocity or the constant acceleration model. So first of all, I give myself a vector. So this is just a vector of time steps. So it's going from time 0. Remember, we're moving up in a 20th of a second each time. So time 0, time 0.05, time 0.1, time 0.15, and so on. So we're stepping forward in time up until the last time, which is 1.5 seconds. The last time period is just before that, 1.45 seconds. Okay. So these are the individual time stamps. So there's a bound of 0.05 seconds between each of these. Now I set up this array CV positions. So this is going to be the positions of the object under the constant velocity model. So initially it's just, and we're going to build up this vector to have the same length as the original times vector, and this will give the position of the object at each time. So I just add on, initially it's just got one entry, it's position 0. So the object is at position 0 at time 0. And see, for the first bound, the initial velocity is the v0 that it had originally, the original velocity that we're given in the question, which was 5 meters per second. So it's stored. That's the v0 value that the worksheet already has. And this time loop here, this carries out the constant velocity simulation. So for each time period in the times vector, which is all the time periods, all the time stamps between 0 and 1.5 seconds, I add a new position, so I append to the CV position array. So the CV position array, constant velocity positions, is initially just contains 0. So I append something onto it, and it's the previous position. So that's the position at the beginning of this bound, plus the bound length, dt, which is 0.05 seconds, times the velocity. Now initially the velocity is that initial velocity v0, and then at the end of each bound I update the velocity to what its position should be for the next bound. The velocity is equal to velocity plus whatever the acceleration at that time is. I've already defined the function a of t times the bound. Okay. The crucial thing here is that calculating the new position across each bound is just this relatively cheap operation of doing the constant velocity times the time bound. There's just one single multiplication here that's involved in updating the position. So actually run that for loop. And that's running through all the timestamps, updating the positions. So we've got this array now, or this long vector, CV pos. So it's showing the increasing positions of the rocket, and it reverses direction somewhere. Yeah, it goes up to position 2.26, and then it's at 2.45, and then it starts to decrease again, 2.24, and then eventually it gets negative at the end. So it looks kind of right. It's moving out and then reversing and moving back. Let me do the same thing, so we'll graph it in a moment and compare the graphs. It's exactly the same people you had an hour ago. Okay. Anyway, yeah. Okay, sorry. Well, that's a good signal that we should break soon. But let's get to this. So we do exactly the same thing for the constant acceleration model. So I got an array here, CA pos, which is the positions under the constant acceleration model. Now here the for loop looks much the same as it did previously, except this time updating the position is more complicated. The previous position plus velocity times the time bound, but also taking into account the acceleration that's taking place across, or the constant acceleration that's assumed to be taking place across that bound. So it's a more detailed calculation that goes into updating the position. So we execute that for loop. And we got this CA pos array, which has a similar structure to before, beginning at 0, increasing up to about 2 point something, and then decreasing down again. So now we plot all three of them together. So that's the blue line is what we take to be the real underlying behavior. And now we plot a load of short lines joining we plot a line from each of the positions under the constant velocity model, and we color all these green. We add that to the plot. Takes a while to do that. So the green plot is made up of many small little lines. So you can see it's a rough approximation to the blue plot. The blue plot is the real underlying physics, if you like. The green trace is the position of the object, assuming that the velocity is constant across each of those short time bounds of 1/20th of a second. Okay? Of course, it's not, because we assume that the acceleration is smoothly changing by that rate of change of acceleration specified in the question. So really the velocity is changing all the time. Assuming it's held constant for each bound at its correct value at the start of the bound, the motion is simulated by that green trace there. If we plot in red, we're adding to the plot the positions under the CA class. That's the constant acceleration model. So we expect this to be a better approximation. So I've added the red plot to the graph. Okay, it's still over. You can see it's still overestimating the position. Right? It's getting the position wrong in the positive direction, but less so compared to the constant velocity. Model. So remember, the red trace is assuming that the acceleration is held constant across each time. So it's smoothly updating the velocity smoothly across the time bounds. It's taking the acceleration into account, but it's assuming the acceleration is constant across each bound. Whereas from the real information in the question, we understand that the acceleration is constantly smoothly changing. So the acceleration will be changing during the course of a single bound. However, the model that produced the red plot there is assuming that it is. Okay. So the blue one is the most expensive one to calculate. The blue positions are the most expensive to calculate because that involves evaluating cubic each time. The red ones really evaluating quadratic at each stage, and the green one just evaluating a linear function at each stage. Okay. So the linear one is the worst behaving approximation, but it's the cheapest to calculate. So it has that advantage. And when you multiply this up by the potentially hundreds or thousands of objects that you might want to simulate in the environment, computation time does become an important consideration. Okay. Okay, so let's stop there for